These days, more companies are investing in autonomous vehicles. From ride-sharing services like Uber to large auto manufacturers like Audi, the industry is booming. Despite growing interest, the technology itself is in a proof of concept testing stage. It's smart, but engineers are working to make it smarter. Turning a manually operated car into an automated one requires data to be acquired and processed the same way humans innately do. Every day, we interact with the environment through sight, sound, and touch. To drive a vehicle, we are also guided by backup cameras and side and rearview mirrors, and by sensors that monitor road conditions and activate our brakes accordingly. The human gives all the gathered data to the brain to process this information and make decisions. Cars must have sensors that can produce such data, as well as smart methods to process the gathered information. That's where signal processing comes into play. Signal processing is about analyzing data and making decisions. To provide very detailed maps of the area surrounding a vehicle, autonomous cars utilize LiDAR or radar sensors. These LiDAR and radar sensors produce vast amounts of data that is then processed in real time. The challenge is in using this data to help the vehicle make decisions just as we would if we were behind the wheel, if not better. Humans understand red means stop and green means go. We recognize and understand a yield sign. We know to pull over if we see and hear police sirens. We understand the context surrounding driving. Autonomous vehicles have to learn these rules, but they also have to learn the skill of prediction, critical for preventing accidents and for smooth and seamless autonomous driving. As humans drive, we predict what drivers and pedestrians are going to do next. We constantly assess the risks and hazards and try to minimize accidents. An autonomous car must do the same. Autonomous cars need to merge multiple types of data from many sensors that allow for fast object recognition, as well as develop the reasoning that translates data and object recognition into contextual understanding from which decisions can be made. Predicting the behavior of other drivers, bicyclists, pedestrians, and hazards should be integrated into decision-making. The promise and success of autonomous vehicles is tied to being able to analyze many data types, more than we have as drivers, to yield better decisions. Signal processing engineers provide these methods to autonomous vehicles. All of our driving decisions are done individually, but with autonomous vehicles, the decisions being made can be distributed and coordinated. It's possible that someday cars and even the road will be able to share data with each other. Road sensors could tell your car there are icy conditions ahead, so it automatically adjusts the way it drives to have smarter and better road traction. It's even possible that fleets of vehicles could coordinate the distances between each other automatically to optimize traffic flow, reduce fuel consumption, and lessen the risk of car accidents. We've come far and have even farther to go, but with signal processing engineers behind the wheel, we can visualize a not-so-distant future when we'll all be letting our cars do the driving. Will you accelerate us into the future of driverless cars? Learn more at signalprocessingsociety.org.
Okay. After we talked about single channel signal enhancement in the frequency domain, we want to extend that to multi-channel signal enhancement in the frequency domain. So we start with signal model, problem formulation, linear filtering in the Fourier transform domain, performance measures, optimal filters, and then also with implementation with the short-time Fourier transform. Okay. Just like similar what we did with single channel, we do it with multi-channel. So it's an extension of the single channel. Okay, so the multi-channel, we have multi-channel, so we have more than a single sensor. And the signal model in the time domain is convolution between the desired source and impulse response from the desired source to the sensor M. So this we call it or denote it as xm. This is the desired signal part in the sensor number m plus noise. And as we defined it in the time domain, this part we try to estimate. So we need to choose the reference sensor. Which one is the reference sensor? Usually we would like to choose the best sensor. If we don't know, we arbitrarily choose one of the sensors. We hope that this one will be the best, or at least not too bad compared to the others. Once we choose, we try to estimate the signal in the reference sensor using the measurements, the noisy measurements from all sensors. And again, also here, we don't try to do the reverberation. So we estimate x1t, not xt, not the desired source, but the desired source as it is measured in the reference sensor. Okay? So now we apply Fourier transform to this model. So after Fourier transform, we have this one. Okay? So for each sensor, we have ymf. The convolution becomes a multiplication, so we get this desired part plus noise in that sensor. Okay? So of course we don't know this impulse response. If we know it, then we can try to do deconvolution, or in the frequency domain to try to divide or to do the inverse de-reverberation or de-blurring or whatever using this filter. So we can try to divide it by this filter and try to make it robust inverse so that we don't amplify the noise. This is a standard way. Okay. So our objective is to estimate x1f from the same from the frequencies, and for simplicity, as we did with the single channel, we don't use the correlations between different frequencies, even though it's possible. If you have a way to estimate correlations between different frequencies regarding the desired source and the noise, and you have a reliable way to estimate them, you can use them. So it will add, if it adds reliable information, you will get better performance. But here, for simplicity, we don't try to estimate because we say maybe we don't know, or maybe it's difficult to estimate, maybe change in time, and so on. And so we simplify things. But of course, you can extend. You can make things, whatever information that you can get, reliable information, you can change your model and add this and try to find solutions or derivations that will use this additional reliable information. And generally, it will improve the performance. If it doesn't improve the performance, it means either that your information is unreliable or you didn't use it correctly. Okay? So here, if we ignore the correlations between different frequencies, we try to estimate x1f to obtain an estimate of this. So ZF will be the output of the estimator. It will be an estimate of x1f. This is a scalar. Using all sensors noisy measurements from the same frequencies. So I goes from I to n. So it's a vector. So we can take this as a vector. So we can define a vector yf that contains for the same frequency f y1 up to ym. So it's the frequency component the same frequency component from all the sensors. And then we try to find an estimate of x1 using a filter. So if this is a vector, we can define a vector h such that we apply it. Let's transpose conjugate. We can define it in such a way, for example, something like this. If we multiply it with yf, we get an estimate of x1. So this is a linear filter. So suppose that you had more information about the correlation between different frequencies. What would you do? So instead of this vector, what would you do? Okay, if you have more information about the relation. So I extend. Exactly. So for each sensor, a sensor M or I here, it doesn't really matter. I can take all the frequencies and then I can concatenate all frequencies for the first sensor, the second sensor, so on. So I will get here a longer vector. And here I will get a longer filter. This is one way to extend it, taking into account correlation between frequencies. Here, I estimate one frequency, f. Maybe, if I use the correlations between frequencies, maybe I want to estimate all frequencies at the same time of x1. Okay? Not single frequency. So what will I do? Here, instead of a vector, filter vector, I will get matrix, filtering matrix. Okay? So the filtering matrix will include and will derive estimation of all frequencies using this matrix. And I can find the optimal filtering matrix for different performance measures. You see, so everything that we learned, you can combine things. I don't teach you everything. You know, sometimes undergraduate students, whatever you teach them, this is what they know, and then you give them an exam based on what they studied. But when you become more mature as an engineer, you don't know only what you learned. You know how to combine things. So you know more than what you learned. Because you can always teach yourself beyond things. You can extend things yourself. So you can combine whatever we studied, you can combine the filters, the methods, the models into more. You can also extend linear method to non-linear method and so on. You can combine things. Don't just know or learn whatever you learned, this is what you know. It's, you want always to develop your knowledge, to combine things. And if somebody else didn't combine these things, you can take whatever you learned and combined, and you added additional knowledge, so you can communicate this with the community. Conference paper, journal paper, whatever. And you look in the literature. Okay, so sometimes you have questions. Suppose that this, what happens? And you ask questions, and then you look in the literature. Maybe somebody has some question. It doesn't mean that this is the only answer. Okay, so you can find different ways to do it, and you ask questions. So you always try every day, okay, all the time you try to learn new things and derive new methods and so on. So you make an advancement in your area, and you don't feel like it's something you work on. It's more like something you explore, okay? So it's something that you work, you feel, okay, I finished now. Now I worked until 6 o'clock. Now I don't think about this. because maybe it means that it doesn't interest you. If something interests you, you think about it all the time, okay? Because it's interesting, okay? And then there are ways to develop new things, and you enjoy. You enjoy from the knowledge, the additional knowledge. So here we gave an example of how to extend it. So this is the simplest way to do multi-channel linear filtering in the frequency domain. So it's the simple way. So when you study something, start with the simplest way. Don't go to the most complicated problem from the beginning, because it's more difficult to get intuition, okay? But you know that we can go further using the other method. So this is the simplest way to take advantage the spatial information. What is the spatial information? It means that we have sensors, different sensors, one, Y1T, Y, okay, and so on. So in the frequency domain, for a certain frequency, we have one Y1F, and so on until YMF. So the relations between two measurements in the frequency domain give us some information about the signal, where it comes from, what happens, what are the reflections, and so on. So from this information, this spatial information, we can obtain a better estimate compared to a single sensor. So the improvement of the using multiple channels, multiple sensors compared to a single sensor, this is the array gain. So array gain in signal-to-noise ratio. We can also get improvement of other performance measures compared to a single sensor. We always ask ourselves, when we add sensors, what is the gain? Because it adds more hardware, more sensors, more A to D or whatever, more hardware, more computational complexity. And we need to see if it's justified. What is the improvement in performance? Okay, so here we define this vector, y, as it contains, for frequency f, the measurement from all sensors. Also, we define x. So x is this measurement of the desired signal. So we see we can write it as xf multiplied with the vector g. G is the transfer function. Is the transfer function from the desired source to each of the sensors. G1 is the transfer function from the desired source to sensor number 1 in frequency f. Okay, so I don't repeat the dependence on frequency, because here we work on a certain frequency. Okay? So G1 is the transfer function from the desired source to sensor number 1, G2 is to the transfer function to sensor number 2, and so on. So we have m generally different transfer functions. What happens if we don't have reflections? Free field, far field. What do you think? These transfer functions are the same or different? So what? So only phase, right. If it's in the far field, only phase. If it's in the near field, we have amplitude and phase. Okay? So if there is a desired source in the far field, the transfer functions from the desired source to each of the sensor, the difference will be phased only. So this is the model. So it's very useful to work with relative transfer functions. So relative transfer functions, we take the vector g and we divide each element in the vector g with g1. So you see we have the relative transfer function with regard to the transfer function from the desired source to sensor number 1. Because once we choose the reference sensor, this relative transfer function it provides us with information about the direction. And the thing is, why do we use relative transfer function instead of transfer function? Why do you think? Okay, so if I go to the previous slide, you see what is nice? I can write y as a function of x. X is the desired source in the origin. Suppose that here we have a desired source. This is xf, desired source. So instead of writing yf, or we call it lower, okay, so we can denote it with lowercase y. So we can write it as g. See, this is a vector. We can g vector multiplied with a scalar x, which is the frequency f of the desired source. Or we can write it as a function like this, x1, which is the desired signal, desired source signal that is received in the reference sensor, multiplied with the vector d. So the difference between g and d is that we normalize or divide it by g1. So what is the advantage of working here compared to working here? Okay, mathematically it's obvious, right? We just write it as multiplication with x, but here we write it multiplication with x1. So what is the advantage? So I want to mention two advantages. Let's think. What is the advantage? See that whenever we use a model, signal model, how it's received, we want to explicitly write it as a function of what we want to estimate. Okay? Makes sense. So we prefer to use this formulation than this formulation because we want to estimate the desired signal in the reference sensor. So it makes sense to write it like this. This is one advantage. Another advantage, another reason that we want to write it like that. You see, G is the transfer function from the source to each of the sensors. D is the relative transfer function. So what I suggest is we don't know G. Maybe we don't know G. So G is difficult to obtain from the measurements, from Y. It's difficult to obtain G from the measurements. But D we can obtain from the measurement. So it's quite useful to write the measurement as a function of D, the vector D multiplied with x1 plus noise. Okay? So you understand these two advantages. So it's a better way. When we write the model, we write it as a function of what we want to estimate, and also using information that we can obtain from the noisy measurements or from other things. But here, we can obtain D, and it's very difficult to obtain G, you see. How can we obtain D? We will see soon in the next slide how we can obtain D in a practical way. But the definition of D is simply taking G, G1, G2, and divide each element with G1. So this is the definition of D. And actually, D replaces it, gives us some information about the direction of the desired source. That's why many times we call it steering vector, because it gives us what is the direction of the source, where it comes from, direction of arrival. So it's a steering vector. Sometimes we call it propagation vector. Okay, this vector. Now, what we can see, that the vector, each element in the vector D, the relative transfer function, can be obtained actually from the correlation between signals in two different sensors. So if we want to obtain the correlation between the relative transfer function G2 divided by G1, we obtain it using the correlation between X2 and X1. So we can write in a general way that the desired signal in the sensor number M, we can write it as, you see, of course, we can write it as multiplied. I will write it like this. Do you agree that XM F equals to GM F divided by X by G1 multiplied with X1F. Okay? From the model. So here what we see, this is the element. The element here, the relative transfer function, in the steering vector, D. So this relative transfer function actually is the same as the partially coherence between these two elements. I will show it. First, I will define what is this term. I will define it. What is the partially coherence between two terms in the Fourier transform? And then I will show how to obtain it. Okay. So first, the definition. The partially normalized coherence function between two elements, two scalars, two complex scalars, is defined like that. So it's the expectation of the correlation between X1 and the XM complex conjugate, normalized by the variance of X1. So this is a definition. Okay? And if I actually put here XM the way it is defined, the way according to our model, I get that this correlation partially normalized coherence function equals to the complex conjugate of this transfer function, relative transfer function. So that's why I can write here a vector. Instead that it contains the relative transfer functions, I can put the vector, which is vector of partially normalized coherence function with regard to the desired source. And the correlation is between X1 and the vector X. Here is the X1 and element of the desired source, XM. So here we get a vector, the correlation coherence function between X1 and X. If it's not clear, I can repeat some of the material. Okay, so if you have questions. And the nice thing is here that we can actually, in many cases, we can estimate it from the data. How do we do it? Suppose that I have some intervals without noise, some data without noise, which means that I have X1 and XM. So do you agree that I can compute this expectation based on clean data? and we can normalize it. So I can obtain this value. It's a complex number, right? I can obtain this relative transfer function from data as long as I have some intervals with clean data. And suppose that the sensor array doesn't move in space, remains the same. And the source doesn't move in space. So everything is the same. So the relative transfer function, or this coherence function, will remain the same because there is no movement, change in space. Which means that afterwards, when I make new measurements with noisy data, I can use this coherence function or the steering vector. Okay? So I can estimate the steering vector or coherence function from clean data and then use it afterwards to apply it with noisy data. If the configuration in space doesn't change, which means that the source comes from the same direction and the array it's in the same position. It doesn't move. If it moves, I need to update. But this is a big advantage because, you see, if I try to find an estimate of the transfer functions, it's much more difficult because I need to know the source signal and so on. So it's more difficult. But the relative transfer function, I can use it from the sensors. So it's much easier. So it's useful in practice. Now, after I define the problem like this, you see, so I can define the problem like this, and I assume that I know the coherence function, or generally I will call it the steering vector. So if I know this steering vector, you see, so this is a vector that contains all measurements for the frequency f from all the sensors. This is a vector of length m. This is also a vector of length m. x1 is a scalar of, see, it's a complex scalar because it contains only the frequency component f for the reference sensor. And v is also a vector of length m. So this is our model, and we assume that we know the steering vector, which is the relative transfer function. Now we want to estimate a scalar x1 from a vector of length m. When did we do that? When did we learn how to estimate a single component, a scalar, from a vector, using a vector filter, linear filter? It's similar to what we did, single channel in the time domain. The only difference is with the single channel in the time domain, everything was real. Here, it's complex. But it's similar to what we studied in the, okay? So we tried in the single channel time domain to estimate a sample, xt, from a vector of L measurements, L noisy measurements. So here, we try to find a single component from a vector of M measurements. So it's similar in that sense, but it's not the same, okay? Because here we need to define different things. The performance measures will be defined differently. We have narrowband and broadband performance measures, just like we had for the single channel frequency domain. So we have different definitions of performance measures. And because of that, we will also have different filters in the Fourier, in the multi-channel Fourier domain. Okay? So there are some similarities, but many other differences. Okay? Definitions, terms, and so on are different. Okay. We discussed this. Now, we discussed the signal model in the Fourier transform domain. So we wrote that, if we go back here, okay, so we wrote that the vector YF, this is the vector of M samples. We wrote it as a vector D, or the complex conjugate coherence function between x1 and x, multiplied with the scalar x1f plus v. Now, the noise generally is composed of directional sources and other sources. So also we can write this background noise, we can split it into two terms. One term is noise terms that are coherent, and other terms which are incoherent with the noise in the reference sensor. So we can write V M. This is the noise component in the sensor M. So if we can write it, we can split it into two terms. One term which is correlated with the noise in the first sensor, and here the remaining noise. Okay? So it's a useful way because these two components are uncorrelated, which is nice. And here also, suppose that we have a directional noise source, so it will be contained here. And this will contain the remaining part. Not only thermal noise, but also some noise which is uncorrelated with the first noise. We can split it into two terms. So this part is the part that correlates with the noise in the first sensor. This part is uncorrelated. We can always do something split like that. Okay? And then we also have here the coherence function between V1 and Vn. We can always do something like that. So we can write the vector V, the vector that contains the noise for frequency f, using a vector, the coherence function between V, the noise, and the noise in the first sensor, in the reference sensor, multiplied by V1, plus remaining noise. So you see also this coherence function, we can estimate its correlation. Under which conditions can we estimate them? As long as the noise sources, at least the coherent noise sources, remain the same directions in space, if they don't move. If they move, I need to track this coherence function. And then updating the propagation vector or the steering vector, it's called tracking. When you have a moving source, you need to track its position. So you can do that. But suppose that its place, position in space, is stationary. It stays the same. So this remains constant. And suppose that the noise also is stationary. So the variance of the noise remains the same, and so on. So I can estimate this coherence function, or the steering vector. It's the steering vector of the coherent noise. I can estimate it from intervals where I have only the noise without the desired source. And here I have the remaining part. So this part will be easier to handle. Why is it easier to handle or more easy to suppress? Because with multi-channel, I have the ability to filter out different directions. So I can do some spatial filtering in such a way that I have higher array gain for directions of the desired source, and low gain for undesired directions, for interferences. So this is like directional interference. And this is incoherent noise, which I can still remove by some ways or suppress. But usually this I can reduce less efficiently using multi-channel sensor array. So this will may create more distortion. Maybe, depends. It's more like averaging uncorrelated noise in different sensors. So by averaging, I can reduce the variance of the noise, but it's very limited, the amount of noise that I can reduce such a way, or I need to use many sensors. Here, directional noise I can suppress by eliminating some directions that I would like to have low gain to that directions using sensor arrays. Okay? That's why it's useful to separate the noise into these two terms. Okay? To see, because if I see that here the dominant noise is in this part, then it's good. It means that I will be able to improve the performance without sacrificing too much distortion. If the significant noise is in this part, it means that the array is not that useful, and probably I need many, many sensors and then to average the signals and steering to the desired source and averaging. And then the reduction of this noise using array processing is limited. Of course, it's possible to do other post-filtering after the array processing. Okay. So eventually, so we write the measurements, the vector of measurement for the frequency f, as composed of three components. One component is the desired source. Second component is the coherent noise. Coherent noise is the noise that are coherent with the noise in the reference sensor. So and then the incoherent noise, incoherent components of the noise. So you see the incoherent noise is 0 in the first element. We have only the other elements, because in the first element, all the noise in the reference sensor is by definition coherent with the noise in the first element. So that's why we have 0 in the first element of the incoherent components, incoherent noise. Questions? So this is the signal model. This is a general signal model for multi-channel in the frequency domain. Multi-channel signal enhancement in the frequency domain. Okay. Now we compute the variance or the coherence metric or correlation matrix of the vector y. So the correlation matrix of the vector y, you see, because we work with complex numbers, so here in the time domain we put here transpose, here we have complex conjugate transpose, Hermitian transpose. Okay, so we have here transpose complex conjugate, and the expectation here, we see that it composed of three components from the previous equation. The first component is the variance of x1, the variance of the desired signal in the reference sensor, multiplied with a matrix. This is a matrix because this is a column vector, this is a row vector, so we have a matrix. So it's a matrix of the steering vector multiplied with the complex conjugate of the transpose of the steering matrix. So this matrix is a rank 1 matrix, see? Plus we have for the coherent noise component, the variance of the noise in the reference sensor, multiplied with a rank 1 matrix that is composed from the coherence function of the noise with the reference noise. And here it's a transpose. So this is also a rank 1 matrix, plus the correlation matrix of the remaining incoherent component of the noise. And this is the rank